Well, alrighty. This problem, there's two problems actually here, both from Miriam. And the first one here is determine the value of the damping ratio. So this is actually a pretty straightforward problem. You could do this problem like in I don't know, I'm guessing 4 minutes. We could time ourselves. We started at the 26 mark. Okay, so determine the value of the damping ratio for the spring constant right here. So it's very straightforward. The only thing that twists is that it's in US units, really. Let's multiply 3 pounds per inch to by 12, so we get 36 pounds per foot. That's a good thing to know. And the weight is 8 pounds right here. So first thing we would do is find the natural frequency, K over M. And as we saw in a previous problem, 8 pounds, no, excuse me, K goes on top, buddy. All right. So we start 36 pounds per foot divided by mass, but instead we have weight, so we need to divide that weight by 32.2, and that ends up coming up back up onto the top, and then all the units work out. So we get 12.04 radians per second. We can find the critical damping is going to be 2m omega n. So we get 2 times, and we have to do it again, right? 8 pounds divided by 32.2, and then times the natural frequency we just found. We get 5 point, I think it is 5 point, yeah, that sounds right. 5.981 pound second feet is their units, and then the critical damping ratio is just C over CC. This is the same unit as this. We get 2.5 divided by 5.981. So this is going to be 0.4180, and we're done in 2 minutes, right? So that was a 2-minute problem. I'm going to ask you questions that are longer than 2 minutes, so I don't want to simply expect something to be that easy. So let's move on to this guy right here, and it says for the 8-pound body in this is released from rest at a distance x naught from the right of the equilibrium position. Determine the displacement x as a function of time. So we want where t equals 0 is the time of release, right? So basically we're going to find an equation. This is an underdamped equation, so that's the form that we will use. And for initial, so here's the basic equation with initial conditions for a spring mass damper system. It looks like E, and I like to use this version, so squiggle NT, squiggle omega NT times initial conditions x dot naught plus squiggle omega n XO omega D times sine omega D T plus x naught cosine omega D T. All right, so that's our form. So we need omega D, and we know that that's going to be omega n times 1 minus the damping factor squared, or 12.04 times the square root of 1 minus 0.4180 squared. We do all that, and we find we get 10.94. Remember that because of the way this is written right here, this equation was written right here, omega D is always going to be less than omega n. So we have this is just a little bit smaller than that. The rest is just plugging and chugging on this problem. There's nothing much more to it. To put this back in there. Notably that it's being released from rest, right? So it's released from rest at XO. We're not given XO, so that's going to be a variable in this in both places, right in here. If we wanted, we could do that. We could end up with we could find the amplitude and phase angle, but let's not bother in here. So we'll write out x of t is going to be e to the minus 0.4180 times omega n. Make sure you use the right omegas. And that's going to be times t. And then we're going to have, in the initial conditions, 0 here, plus 0.4180 times, once again, omega n. Whoops, that looks like a 7. 12.04. And then this just has an XO, right? Because we don't know what they just said for some distance here. But we are going to divide by omega d instead of omega n. And then we have the sine of 10.94 t plus, okay, now we have XO right here. Once again, we don't know what that is. Oh, we know what the omega d is, though, right? So 10.94 times time, close bracket. So here is sort of our final answer. I'll put the XO. I'm bringing him out from both of these things. I hope that doesn't bother you, that I skipped writing it out again. It's going to be negative 5.0. I think it looks like a 3, my handwriting. We need a bracket. This magnitude in front of the sign is a 0.460. And the sine of, now we're just writing out the rest of the stuff. We already took out the XO, so the cosine is got nothing in front of it. And we are done. I don't know. It was just a problem. I selected the problem before seeing what the answer was. I'm not sure it's all that exciting as a problem, but it does, we kind of work through and recognize what you need to do. Sure. Let's go on to another problem. See you soon.